Okay, we will get started now. Good morning, everyone. Good morning, good morning. Seeing all the good morning messages in the chat. Welcome to this UK Data Service workshop named Mapping Crime Data in R, an introduction to GIS and spatial data. Just a quick introduction. My name's Nadia Kenner, and I'm a research associate with the UK Data Service based at the Marsh Institute at the University of Manchester. Now, this presentation will be treated as an introduction to the main topics and issues involved with GIS, which refers to graphical information systems, and mapping data. It isn't going to provide a huge array of information, but it will detail what is necessary to follow along with the code demonstration, which is happening tomorrow. So, in today's workshop, we'll be exploring a few topics. We'll be looking at what exactly is GIS, the differences between spatial data and non-spatial data. We'll look at the different types of maps that are available, including reference and thematic maps. We dive into projection methods and coordinate reference systems, which kind of is a bit more complex. And then we look at different types of spatial relations and spatial statistics. I talk about spatial autocorrelation, spatial interpolation, and hotspot analysis. I do also mention point analysis in the latter half of this workshop. And then we'll talk about some data sources that are available for crime mapping. And lastly, we'll have a bit of a conversation about the challenges of mapping crime data in general. In part two, tomorrow's workshop, happening also at 11 a.m., this is where we run a live code demonstration. I will be walking you through four main topics in R, it's IDE RStudio, where we'll first be looking at exploring crime data. This will be a very descriptive topic. We'll look at point maps and we'll look at what exactly are SF objects. In topic two, we dive straight into shapefiles and how we join this to our crime data, and we start to make these really cool classification maps using tmap. And then we move on to looking at census. This is probably the shortest topic of the four, but it allows us to move from mapping raw data to mapping crime rate data and how we can move these into making cartograms. And then in topic four, we run our spatial analysis. So this involves looking at spatial interpolation and also producing heat maps using ggplot2 and leaflet. And then given how much time we have, and following on from some feedback from previous workshops, we'll be looking briefly at the Google API and how we can make maps using this, and also running some time series analysis with rolling averages, which basically involves exploring more than just 1 month of data. The material for the code demo can be found at our GitHub repository. Emma Green will just plug that into the chat for you as well. But towards the end of this workshop, I will demonstrate to you how to get this code on your own computer screen. So yeah, don't worry about that too much now. I'll show you how we can either clone the repository or how you can work from the cloud-based environment. And yeah, again, I'll explain this at the end of the workshop. So, what exactly is GIS? GIS stands for Graphical Information Systems. It's a computer system for capturing, storing, checking, and displaying data related to the position on the Earth's surface. It can be seen as quite a abstract framework or a theoretical framework that allows for the creation and analysis of spatial and geographical data. It allows us, or it's basically a platform that allows us to integrate data onto a map using various statistical methods. Now, GIS is present in virtually every field and every organization. It's a way to share information, to solve complex problems, but the biggest benefit is allowing for trends and patterns to be studied visually, which provides this new form of analysis. Now, just a little background about GIS. It was actually first coined by a pioneer and researcher named Roger Tomlinson back in the 1960s, and he was commissioned by the Canadian government to create a usable and efficient inventory of its natural resources. He tried various manual methods for overlaying these variables, but he found that all were too costly. So he basically helped to create the first automated computing system, and he was therefore known as the father of GIS. And this image that you see on the screen is one of the first maps that he did produce. And from there, we've got researchers who have, of course, extended this, such as Laura and Jack Dangermond, who developed the Environmental System Research Institute, also known as ESRI, which is the software developed for mapping and spatial analytics. So it's important to note that most datasets you encounter in your life can all be assigned a spatial location, whether on the Earth's surface or within some kind of arbitrary coordinate system. So the question you need to ask yourself is, does it need to be analysed in a GIS environment? If we take a look at this example on the screen, I've produced two questions for you. So imagine you are interested in question A. You are interested in identifying the 10 cities with the highest average income scores. As you can see, we've got a very simple table here with two variables, our cities and our scores. We can, of course, answer the question A using just these. However, if you are interested in answering question B, which is if you're interested in identifying whether these 10 cities are geographically clustered, we might struggle to answer that question with the data that we have here. And this is because we need some more information, specifically about the shape of the country and the geographical location. In that instance, we might have something that looks like this. We now have three variables, including the city, the score, and the spatial boundaries. And this provides us with the shape and the geographical location that allows us to basically map those scores onto a map. Geographical information contains either an explicit geographic reference, such as latitude and longitude, or national grid coordinates, or what we call an implicit reference, such as an address or a postal code. All data in GIS are georeferenced. You'll either georeference, meaning it has both the attribute, as in what it is, and also the location. For crime data, an attribute might include who/where the call was received, or even just information about the type of crime recorded. But yeah, just to let you know, an automated process called geocoding is used to basically create these references, and these geographic references allow you to locate features and events on the Earth's surface for analysis. So it's kind of like a universal logbook where everything is given a set location. Now, there are various softwares available for GIS and spatial data. In this workshop, of course, we'll be using R and its IDE RStudio due to the increasing amount of packages that have become available for spatial analysis and mapping. And I really believe that R has increased its efficiency over the last few years as an analytical tool, and I really do support its promotion. But another very, very strong program language would be QGIS. It's free and it's open source, which is a big deal for budget constrained police departments, and it has a strong spatial analysis tool. You can run things like hotspot mapping, kernel density estimation, buffer analysis, and it supports a huge range of data formats. There's also a really large plugin ecosystem with QGIS, including tools well suited to crime mapping like it's called the QGIS and the heat map plugins. But arguably, the learning curve for QGIS can be quite steep. But we could say that about any program language. But just being a little bit nosy, I wanted to know what software have you/do you use for GIS/spatial analysis and mapping. This could be in the past, this could be what you're working on now. If you haven't used anything, then please just say nothing. And this is just going to give me a bit of an idea about where we are today and yeah, what level we'll be working at tomorrow. Nothing's coming in quite strong, which is absolutely not a problem. I hope everyone obviously has read the prerequisites for this workshop. There is some basic understanding of R/RStudio needed for tomorrow, but again, I'm going to show you a demonstration about how to get get RStudio set up today. We've got quite a few users saying ArcGIS. It is very user friendly, I will say that. It's got a very intuitive GUI that makes it accessible for users of all levels. It does provide extensive documentation, tutorials, and community support, and it also integrates well with other Esri products and services. Um, Python's coming in as well. That's pretty interesting. Funny enough, I've never been a big Python fan for when it comes to mapping data. I feel like it lacks its visualization tools, but that could just be me being biased because I've always used RStudio. Um, but I do feel like Python just requires a bit more extensive um, like background programming, there's a bit more of a steeper curve. Anyway, that's great. Thanks everyone for filling that in. That was me just being a little bit nosy. So let's keep moving. Oh, sorry. So, how exactly is GIS used? Well, Esri defined 6 points for how GIS is used. And these are summarized in identifying problems, monitoring change, managing and responding to events, perform forecasting, set priorities, and also to understand trends. So let's think of a few questions that GIS allows us to explore with crime data. So we're going to move to kind of adopting this kind of crime lens, and we're going to take these research questions and understand why GIS is used to explore crime data. So let's say, for example, you're interested in where are the most vulnerable communities located. Let's just say that individuals want to use crime maps to safeguard their personal safety. So let's say we want to avoid areas with a high level of street robberies, then clearly a geographical representation of crime would be really, really appropriate here. Maybe you want to use GIS to understand why crimes occur in one area and not the other. Now, if you come from a criminological background or a sociological background, you'll know that there are lots of crime theories that explain why crime occurs in some places and not the other, such as the routine activity theory, situational crime prevention theory. What else is there? There's the broken windows theory, crime opportunity theory, but also the crime pattern theory. And this one specifically integrates crime within a geographic context that demonstrates how the environment that people live in and pass through influence criminality. So this theory specifically focuses on place and that lack of social control that are informally needed to control crime. So let's say, for example, a urban or even a suburban neighborhood, it could become a hotspot for burglaries because some homes have that inadequate protection and nobody home to guard the property. Maybe you want to use GIS to understand why or how offenders travel to the crime location. In other words, what is it about one specific place that convinces an offender to commit that crime there over an alternative location? Um, Now, there are a few reasons that affect how far an offender travels, and there has been some research done on this topic already. For example, there was a study done by Ackerman and Rosmo in 2015, and they found that in general, violent crimes had a shorter median distance to crimes than property crimes, which is really quite interesting. There's also other factors such as age and gender, and also things like neighborhood affluence and target suitability that affect how offenders travel to the crime location. You could lastly use GIS to explore where are there more or less stop and searches than we would expect in relation to the distribution of crime. So by comparing this actual distribution of crime and the level of stop and search, we can start to question the necessity of stop and search. We can start to question whether it's just a tool of crime reduction or a tool for crime detection. Or, you can start to question the police powers, etc. But yeah, this was just a little bit of a theoretical understanding of why GIS is really, really important for understanding and exploring crime trends. So, GIS are known to produce two broad types of maps. These are known as reference and thematic maps. Reference maps are used to communicate location on more static data points. It's basically to pinpoint data on a map, and it's rather descriptive. Thematic maps, however, are used to highlight a spatial relationship. So this is to study a theme within a map. And this is where it becomes a bit more exploratory. Just to take a look at a very quick example that I created. The map on the left is what we see as a reference map. It's simply a map that highlights natural patterns or synthetic features, including the positioning of heights, the layout of countries, and this type of map is simply referencing what exists in our physical environment. It is just telling us what is there. The map on the right-hand side, it looks a bit distorted, doesn't it? Now, this is a this is a map of Africa. But as you can see, the countries within the continent do not really look like this at all. But this map is highlighting a spatial relationship. It is showing us how we can map a particular theme to a geographic area. It tells us a story about a place, and it's used to map things like climate issues and health issues. And in this example, it is mapping population density. Now, sometimes the difference between reference and thematic maps can become confusing. So I wanted to take a look at a more realistic example, a real example. This is a project called Lives on the Line. It was done back in 2012, I believe. Um, Now, typically, most government statistics are mapped according to what we call official geographical units. So this can be things like wards, boundaries, or lower layer super output areas, which is exactly what we'll be using tomorrow. Now, while these units are essential for data analysis and making decisions, especially about policy, for many people who, don't have that crime background or that spatial knowledge background, um, these typical units don't particularly stand out on a map to us. And this is why they tried a new method. They wanted to show life expectancy statistics in a fresh light by mapping them against London tube stations. So they had London tube stations as their main unit of analysis, which is really cool. Now, you might think automatically that this is simply a reference map, or you might think that this is a bit of a thematic map. It can be a reference map because it shows the locations of different tube stations and the locations of each tube line, right? It is referencing what already exists. But of course, it does move one step further into the thematics maps because it's being used to predict life expectancy, also poverty and median house prices, which weren't shown in the previous slide, against tube stations. You can have a go at exploring this by following the link Lives on the Line. But yeah, this was just a really cool example to show you an example of a thematic map. What I wanted to do now is give you guys some time to have a bit of thinking space and stop my yapping. But I've come up with a few scenarios where I want you guys to basically answer whether you think that this is a type of reference or thematic map. So, in scenario one, the visualization of road networks to improve road safety measures can be seen as a type of what? Can this be seen as a reference map? Can this be seen as a thematic map? Or if you're unsure, please put in unsure as well. There are no right or wrong answers. We're all here to learn and we'll be discussing the answers very shortly. So yeah, I'll let a few answers roll through and then we'll have a little chit chat. So at the moment, the majority of responses are saying that this scenario is a type of reference map. And we've got a few saying that this is a thematic map, which is pretty cool. But yeah, this type of scenario is actually what we would call an accident analysis. We are visualizing the road networks to improve road safety measures, right? So you can break this down into two aspects. At first glance, yes, this can be said to be a type of reference map because we are simply pinpointing existing road networks onto a map, right? we are referencing what already exists in our physical environment. However, this might be said to be a type of thematic map because what we are actually doing is studying the existing road networks to then improve road safety measures, which can be seen as a type of accident analysis. So let me give you guys an example. This could include the introduction of speed signs or zebra crossings outside schools or residential areas due to reports of accidents or dangerous driving. So, yeah, we are studying spatially the relationship between the road networks and the accidents. Therefore, we are mapping a particular theme to a geographic area. So, for those 6 who said thematic maps, congratulations, you are correct. But for the rest who also said reference maps, you are also correct. Move on to scenario 2. The visualization of the Earth's surface showing its elevation is a type of what? Do we think this falls into the definition of reference maps, thematic maps, or again, if you're unsure, absolutely no issue with that response either? That's great. Okay. So the majority of people are thinking that this is a type of reference map, and we've got a few people who are also thinking this could be a thematic map. So let's break this down. The visualization of the Earth's surface showing its elevation is what we would call a topographic map. Now, this refers to the graphical representation of the three-dimensional configuration of the surface of the Earth. In short, it is simply describing where the Earth's surface is elevated. And these are normally represented by those contour lines that we see on maps. So yes, this would be a reference map. However, dun dun dun, you might also see that this is a type of thematic map. And this is because researchers suggested that studying a topographic map is a great way to learn how to match terrain features with the contour lines on a map, such as the steepness of the terrain, whether it's above or below sea level, the shape of the terrain. So in this instance, you might interpret that what you are studying spatially is the relationship between the contour lines to the different features of the Earth. So if you answered any of the options, you can consider yourself to be correct. But the answer is up to the debate. You know, it is dependent on your aim in using that map. And it's a difference between mapping places and kind of mapping data. I believe there's just one more scenario. Navigation tools, Apple Maps, City Mapper, Google Maps. Can these be classed as reference maps or thematic maps? I'll give 30 seconds just to answer these again. Okay, great. Looks like the majority of people are thinking that a navigation tools can be seen as reference maps. Let's break this down. So yeah, immediately you can assume that this is an obvious type of reference map, right? Because all it's doing is highlighting important physical features needed for travel, such as bus routes, walking routes, tram routes, cycle lanes, etc. So yes, yes, I would say that navigational tools are predominantly reference maps. They're simply referencing what exists in our physical environment. However, dot dot dot, reference maps portray a basic set of features, right? Such as terrain and transport routes. Some even show coastlines. So can we say that an app that plans your travel is a type of reference map? You know, it uses some sort of AI algorithm to get you to one place to another, right? Normally choosing you the cheapest or the fastest route. So can we call this a thematic map instead, since it's overlaying information onto our reference map? And this is really interesting and brings us back to Roger Tomlinson, the father of GIS, and his automated computing system. It draws importance to the differences between analog and digital maps and their place that they have in GIS. So recently, researchers considered navigational tools to be fundamentally different from both reference and thematic maps, which kind of opened debates for a third category. But it could be argued that all maps are navigational, right? Just depending on how we use them. The difference is that a digital map, so one that is specifically interactive, sorry, yeah, the difference is that a digital map is specifically interactive. So this links us back to the Roger Tomlinson's work. You know, he can overlay his data onto an analog map and move towards his computation. So one main difference between the reference and thematics maps is that these thematic maps tend to be more interactive, which is why navigational tools might be considered to be a type of thematic map. So again, if you answered both, you can consider yourself to be correct, but the answer lies in how we end up using that map. So just to sum up, um, although maps fall broadly into these two categories, there are ways in which these types of maps tend to overlay or overlap or even share similarities. We can say that almost every thematic map, so that's one that has a spatial relationship, is also a reference map, right? Because it's going to have that base layer information of the physical environment. But not every reference map is seen as a thematic map. The decision is up to you. And it's not entirely necessary to define these in your work, but it's important to understand or to know what type of map you have, as these can be affected by the data that you have. Back to the Mentimeter. Can you give any examples of any other types of map that you think share qualities of both reference and thematic maps? I realise that we might have a few beginner users in the themes of GIS and mapping data. So if you're not familiar with any types of maps, that's absolutely fine. But I'll give this 30 seconds to a minute. If anyone's feeling confident, whack them in, and if not, I'll run through some examples and what types of map kind of share these themes. I'll just give one example to maybe get things going, but crime. Oh, stole it off me. Heat maps. There we go. Perfect. This analyzes where um, crimes are most prevalent in order to like reduce crime or then, introduce slash amend policy, and it can become thematic. IMDb deprivation. This is great. Yeah, this overlays kind of deprivation statistics over a base map over certain areas, which helps us identify which areas are high or low in deprivation statistics. Meteorological maps and weather maps, exactly. These are providing further information about our physical environment and the relationship to weather. So, um, this changes daily and this becomes what we call continuous data over raster maps, which we'll get into a little bit. Um, that kind of falls within our topographical maps as well, with the example that I provided earlier with the Earth surface. A given disease map, yep, exactly. That's another great example. Other types of specific maps include things like choropleth maps, which we'll dive into tomorrow, cartograms maps, dasometric maps, flow maps. What else is there? Trying to reel these off the top of my head now. Oh, treasure maps, fantastic. Poverty maps, flood maps, these are all great examples. 3D maps such as population, that's a great one. If you're referencing like population densities, if that's what you mean, great example. But as you can see with all of these examples, it's simply putting a theme onto a map, which obviously includes that kind of thematic spatial analysis and that thematic spatial relationship against a reference map. You might have also interchangeably heard me say reference and base maps. Those are synonymous and those can be the same thing. Population, constellation maps, all great examples. We'll just give this another 15 seconds or so. Okay, that's great. We'll move on from there. Those are some really good answers. Thank you for participating in that Mentimeter. I know the open questions can be quite intimidating in a workshop, so I appreciate the interaction. So, what is spatial data? Now, we briefly spoke about this at the start of the workshop, where we mentioned that we need to have some sort of spatial boundary present in our data set. But spatial data is just simply a data frame that, again, contains the information about a specific location. which can be analysed to better understand that location. And GIS, that theoretical framework, allows this spatial data to be processed and analysed. Spatial data can be broken down into kind of two types of data, and these are known as vector and raster data, or raster data, depending if you're from the south or from the north. I say raster, some say raster. Say it how you want to say it. But they are two very, very different file formats that are used to store uh, geospatial data. So let's take a quick dive into the differences. So vector data is the most common file format, and these consists of points, lines, and polygons. Now imagine points are simply a pair of coordinates. So in the crime lens, this could be the location of a burglary report, for example. Lines then extends the point and they include at least two coordinates. This could be, for example, the street that that burglary report was received on. And then polygons extend the lines, and this includes three or more points. So this could be the area, the city, or the ward that that street belongs in. So imagine it as imagine you're like your local corner shop, your local Tesco's, your local Sainsbury's. You're zoomed in onto a map and you zoom out a little bit more and you see the street that that shop is located on. That would be the line. And you zoom out a little bit further and you see the area that that shop is located in, and that would be the polygon. And we're going to dive into points and polygons in tomorrow's code demonstration to get a kind of better understanding about what exactly these are, because of course the easiest way to understand these concepts is to put them into practice. We then have our raster data, and this normally refers to imagery or satellite data that are formed from a grid of pixels. Now, it's not of relevance to us in the crime data world, and this is because raster data typically represents data that changes continuously across a landscape. So they provide an effective method for storing the continuity of surfaces. They basically provide a regular spaced representation of surfaces, and these are things for like temperature or elevation, where each pixel represents a different value or attribute within the overall range of values for that data. An interesting point about this type of data is that you can't manipulate the information. You can't move a place name around, for example, and when you zoom into that map, it quickly becomes pixelated and unreadable, kind of like a photo taken on a digital camera. But again, this is not of interest to us, but I did just want to pinpoint the two types of spatial data. So if we move on to looking at GIS data management. Now you'll encounter many different GIS file formats for both vector and raster data. The most commonly used file format for raster data is what we call GeoTIFF files. Again, we will not be touching on these, but I just wanted to draw your attention to it. And then the most commonly file format for vector data is what we call a shapefile. This image below is a file extension of a shapefile. And yeah, it's used for, as we said, discrete features like crime locations, street networks, administrative boundaries. And when we said that vector data contains three geometry types, the points, the lines, and the polygons, right? A shapefile is not a single file, but a collection of files that keep together these three geometry types. So, for example, in the .shp file extension that we see here, it's marked as a feature geometry. And this is the point, the lines, and the polygons. And this is where those are stored. You then have the .dbf file, and this stores attribute information. So this could be things like the crime type, the day it was recorded, the street it was recorded on, the severity of the crime type, actions involved, kind of all those like additional things that you want associated with your crime type. Um, Another important file extension is the .prj, which reference our coordinate systems, which is essential for the spatial alignment. And we're going to talk a little bit about coordinate reference systems in the next few slides. And I wonder what else I should mention. The .shx file extension is what we call a feature geometry index. And this is basically the index that links the geometry to the attribute data. So I'd say that those are the four most important ones to know. The remaining files are optional spatial and attribute index files that can improve query performances, but they aren't completely required for the shapefile to load. Um, yeah. So yeah, now we understand how shapefiles are structured. Let's have a quick look at how R pulls all of that together in a single line of code. When in R, we use something called SF, or the SF package, and this stands for a simple feature. Again, it's a name, it's referencing the feature geometry. So a simple feature is essentially the modern R-friendly way of handling the same vector data that the shapefile stores. And here's how to think about it and link the two. So yes, we use this package called SF, and it's just a modern approach to managing the spatial data. There are many other packages, including ggplot2, tmaps, leaflet, dipler, janitor, and we're going to touch on all of these tomorrow. I do believe we go for about 10 packages in tomorrow's workshop. Um, but as you can see in this quick code example, we're simply loading in the package using the library function. And as you can see, I'm calling on a new object called shapefile, assigning this, well, I'm assigning it to an object called shapefile, and I'm using the function st_read from the library package. And yeah, reading in that shapefile. As you can see, this is notified by the .shp file extension. So if we go back to that file format, that is the feature geometry. That is the point, the lines, and the polygons. That's exactly what we need to map crime data. In the latter part of this code, we also see how we are transforming the shapefile into the correct coordinate reference system. And you might be thinking, I have no idea what that means. I have no idea what you just said, but that's okay because we're going to talk about that a little bit later on. But it basically just ensures that all spatial data is aligned properly. When working with spatial data, you have to make sure that you have the correct coordinate reference system in place in order to make accurate maps. And then this last bit of code just basically is a very quick example about how you might plot a map, which typically uses the ggplot and the geom_sf function. Now, while vector data excels in representing the geometry of spatial features, it does introduce us to a very complex interplay between spatial accuracy and spatial analysis. And this interplay is where we encounter the modifiable aerial unit problem, which is a fundamental challenge in spatial analysis that affects our interpretation of spatial data. The MAUP refers to the cartographic representation of data whose attributes are significantly influenced by the spatial scale used. Let's break that down. In short, in layman terms, we're saying that the same basic data yield different results when aggregated in different ways. And this applies to kind of any form of data analysis, not just crime mapping, but when you aggregate data in different ways, of course you're going to have different results. And there are two aspects to understanding this modifiable aerial unit problem, which is known as the scaling effect and the zoning effect. The zoning effect is also synonymous with the term aggregation effect. So if you hear me using both, just please remember those are synonymous. But yes, the scale effect is simply saying that changing the size of the spatial units, so maybe we start from neighborhoods, but we move to districts, can basically alter the statistical results, such as the means or the totals. So that's the effect of the aggregation, right? And then you have the zoning effect. And this is where altering the shape or the configuration of the spatial units, even if the scale remains constant, can also impact the result. We show this with a very, very quick example. In that top map, we see the scale effect. We see how the level of aggregation affects analysis. In that left map, we see far more areas, and on the map on the right, we see far few areas. And this is because in the left side, we're aggregating at a aggregating crime at a neighborhood level, and on the right-hand side, you're aggregating crime at the city level, which of course will give different insights, because it could say that a high crime district might, basically a high crime district like might disappear when aggregated to larger regions. With the map on the bottom, the zoning effect, the this is the way that we draw boundaries affects these results. So, for example, changing the police districts may change the crime hotspot rankings. Crime rates might appear lower or higher depending on how the zones are drawn. So, as you can see in this example, there's three maps where all the zones are drawn differently. But where those yellow points are, which is the location of crime reports, you can see how they are affected depending on which boundaries are drawn. And yeah, so each new district basically averages these characteristics of the neighborhoods it combines, resulting in like generalized view that masks different neighborhood level variations. Um, and again, this exemplifies how the method of aggregating spatial units can influence interpretation of the data patterns, potentially obscuring important local details. This was just a quick research question I put together to kind of help us understand the difference between the two in more of a crime lens. So, an example of a scaling effect. A researcher analyzes burglary rates in Manchester using ward level data and finds that the city centre has the highest rate. When they rerun the same analysis using the local authority data, the city centre rate appears much lower and more evenly spread across the city. This illustrates the scaling effect, as changing those aggregation units will inevitably change how we interpret that data. An example of the zoning effect. Two researchers use exactly the same stop and search data for London. Researcher A groups the data by borough and finds that there's a strong north/south divide in rates. Researcher B groups the same data by policing neighbourhood boundaries and finds that the pattern disappears entirely. This geographic scale is the same, only the boundary lines differ. What does this illustrate? This is the zoning effect. So I hope that gives you a bit more of a idea about the effects of the modifiable area unit problem. And the main reason I wanted to address this in this workshop is because when we are analysing crime data, we have the power to choose what our researchers see. We are visualising results onto a map, and we have the power to influence what our readers see. So it's very, very important to understand the differences in which aggregation level you choose to use, and also which boundary lines you choose to use. In relation to kind of crime spatial analysis, can you think of any other potential implications of ignoring the modifiable aerial unit problem? We'll give this about 5 minutes or a couple minutes, and then we'll move on to the second half of the workshop. I'll start with one example, maybe just to get things rolling, but ignoring the modifiable aerial unit problem can lead to a misinterpretation of statistics. For example, what appears to be a crime hotspot at one scale might not be identified as such in another. And this can mislead law enforcement and policymakers where resources are most needed. Lack of trust, exactly. Great example. Inappropriate policy recommendations, which is fundamentally important for crime analysis. Nuanced trends are missed, exactly. If we aggregate to large unit of analysis, so maybe we're just comparing country by country, of course we're going to miss trends within that country, aren't we? The data is skewed and misrepresents it. Size of a grid and producing a heat map, yes, exactly. Um, Misled policy recommendations. That is probably the biggest issue with the modifiable area unit. Law enforcement agencies rely on spatial analysis of crime to allocate resources effectively. And if this MAUP is not considered, then there's a huge risk of misallocating these resources, either by focusing too much on areas that appear to have high crime rates due to the aggregation effects, or simply by like overlooking areas that actually need more attention. Effects on house prices, that's a very great point. If we're kind of taking the yeah, actually, that's a great point, and it's not something I've even considered, the relationship between house prices and crime as well. Um, you might have a researcher who's shown that house prices are significantly higher in one area because they've chosen to use boundary data, but when you use police districts, they might have completely different results. I'm just wary of time, so I'm going to move on very shortly, but please feel free to keep, filling in the answers. And yeah, we will I will upload all the slides at the end so people can continue to basically put in answers, but uh undermine the effectiveness of different interventions. They fail to address the root cause of the issue. Yes, definitely, it's kind of providing a holistic generalization of where we think crime is as opposed to the actual root cause of it. It ties into kind of those ethical considerations as well. Um, yeah, we'll get moving because I'm just realizing the time, and I do want to demonstrate the GitHub at the end. So let's get going. Um, what I will do is actually just give 2 minutes for a break. I need to just grab some water, and yeah, it will just help us flow nicely into the next topic. So we'll be back in literally 2 minutes. Call it at one past, two past. I'll be right back. And if you have any questions, please feel free to pop these into the Q&A now, and I'll do my best to answer these at the end. Okay, we're gonna get going with the second half of this workshop. We still have a fair bit to get through, and we've got about half an hour left. So yes, let's move on to more of the arguably the complicated parts of GIS and spatial data. Um, So we have a basic understanding of the spatial data, but this is where we have to ask, how do we actually pinpoint a location to a map? And the answer is, well, I mean, the question is, how do we move from the 3D to the 2D? And I hope you appreciate my little drawing on screen. Um, but this is where we look to our map projections. And these map projections basically try to portray the surface of the Earth or a portion of the Earth on a flat piece of paper or computer screen. So in like very layman terms, yes, the map projections help us transform the Earth's spherical shape to a planar shape. Now, you always like to use the example of a football. Imagine you have a football and you begin to cut it up with a knife. You would have something that arguably looks like this in the top right-hand corner. Now, if you had tried to recreate this into a rectangle or a square, it would not fit together perfectly, would it? So what these projections try to do is they tell a mapping system how to populate a new shape or area. So if we wanted to create a rectangle, like we see on the bottom of this slide, we might have something where the whole area is populated. So yeah, A mapping system, a projection system, sorry, simply helps us to populate a new area from moving from the 3D to the 2D. Now, it's important to note that during this projection method, the data can become distorted. And this brings us on to our topic of distortion. And this is the misrepresentation of area, shape, distance, direction, and direction of points. Which makes sense because if we are moving from a 3D object to a 2D object, of course, there's going to be differences in these four components. Now, there are algorithms in place to kind of control for this, but all four features are rarely preserved. I like to use the example of imagine you had a map projection as an attempt to reconstruct your face in 2 dimensions. Some maps will get the shapes of all your features just right, but not the size. Like maybe your forehead comes out far smaller than it usually is. Other maps will try to get the sizes just right, but the shapes will be stretched, so maybe your mouth is much wider than it normally is. Um, yeah, so these projections try to kind of control for this, but it isn't always guaranteed. Um, so it all depends on which attributes you're basically willing to compromise, you know. Some try to maintain the correct distance, others the correct shape, but typically you aim to find a sweet spot, some sort of balance between all these factors. But this is why you see projections that are there are different projections for individual countries, regions, or districts. And I'd like to draw on to one example. We move. Um, oh yeah, sorry, just to let you know that there are three kind of projection families known as the cylindrical, the conical, and the planar. Within each projections, there are quite literally hundreds to thousands of different types of projections, that there aren't just three or four. And they're of course not necessary to know. Um, but here is an example of how the same maps can be distorted because of different projection methods. So let's have a quick look at this example. You've probably used the Web Mercator projection, which is the map on the left, without even realizing it. This is the projection behind Google Maps, OpenStreetMaps, Citymapper, and everything like that. It is the most interactive maps you'll encounter online. And it's popular because it preserves the shape of the places, which makes it great for navigation. The downside is that it significantly distorts the sizes, and this gets worse the further you move from the equator. Now, the most famous example is on Greenland. On a Web Mercator map, it appears roughly the same size as Africa, when in reality, Africa is actually about 14 times larger than Greenland. Controversially, the map on the right, which is the Gale-Peters projection, flips this trade-off. It preserves the area, meaning that every country and region is shown at its true relative size. And the cost is that shapes become distorted. You'll notice that countries look taller and narrower than we're used to seeing them. So why does this matter for crime mapping though? You know, if you're comparing rates across large or international areas using the Web Mercator, you risk giving misleading impressions. So regions near the poles will look larger and may appear to dominate the map, even if the actual crime rates are relatively low. Um, so the simple rule of thumb is use the Web Mercator when you need people to navigate, and consider the Gale-Peters or similar area preserving projections when you're making comparisons, such as crime rates across different regions. So how do we actually make this move from the 3D to the 2D? This is where we're drawn to our coordinate reference systems. Um, they move from the 3D, a coordinate reference system is essentially an agreed framework, a universal framework that tells us how to describe locations on Earth. So this is where everything is assigned a longitude, a latitude, or an altitude. The key thing to take away here is that a coordinate reference system are just numbers. This is what gives them meaning and ties them to a real location on Earth. There are two main types of coordinate reference systems. These are known as your geographic and your projected coordinate systems. The geographic is defined as the where. It defines the locations on the surface of the Earth using longitude and latitude. And then the projected coordinate system, which is the image on the right, is the how. It takes the geographic coordinate systems and projects them onto a flat surface, converting these kind of angular units into a linear one like meters or kilometers. Um, the practical implications for your work is that when you're joining datasets in R, both datasets need to be in the same coordinate reference system. Otherwise, your data won't line up correctly. And this is one of the most common sources of errors for beginners. So it's very, very important to know. Um, but in short, the GCS does the heavy lifting of locating you on the globe, and then the PCS translate that into something you can plot onto a flat map. And again, none of this is, calculated manually. There are packages in R that do this automatic process for you, but it is very, very important to know the difference between the two. This slide just brings together everything we've just covered. This details the differences between the PCS and the GCS. And remember that a PCS, which is the projected coordinate system, is just the coordinate system that has been projected already. So in this top example, we see the projected system, and this tells me how to draw the Earth on the flat surface. And in this bottom system, which is the geographic, this tells me where on Earth the data should be drawn. And so in practical terms, when you load a dataset into R tomorrow, we'll check its coordinate systems, and what you're really asking is which of these systems is the data using? And if the two datasets give different answers, you'll need to reproject one of them before you can even combine them. And we'll see how to do that tomorrow. Yeah, that's kind of all we need to know for the coordinate reference systems. It's much easier to run this in a demonstration tomorrow, and I will give more information on this tomorrow. We're going to move briefly on to looking at spatial analysis and spatial relations in GIS. Your spatial relations are about how locations relate to each other, right? Are two areas next to each other? Do they overlap? Does one contain the other? And then the spatial analysis refers to studying these entities by kind of examining and assessing and modeling these features. So let's take a brief look at the three most common analysis methods you might see when working with crime data. The most obvious one is, of course, your point pattern analysis. And this takes us back to our vector data where we look at that first format known as points. And this is a fundamental spatial analysis technique. It's the most straightforward, and it usually involves basically where each dot on a map represents where a crime was recorded. And this is defined by the latitude and the longitude from your shapefile. So the question that point pattern analysis tries to answer is whether those points are randomly distributed, clustered together, or if they're unusually spread out. And in crime research, this clustering is almost always what we're interested in. We want to know whether these burglaries are concentrated on particular streets, or maybe if antisocial behavior is grouped around specific areas. And just by visually plotting these, we can get a very, very intuitive sense of anything before we even apply formal statistics. Your point pattern analysis is more or less your descriptive statistics that you would run in any form of secondary data analysis. Next, we have our spatial autocorrelations. So this map tends to group areas with similar crime rates together. It uses shades of a single color to represent different levels of crime rates, showing patterns of clustering. It basically takes point pattern thinking one step further. Do neighboring areas tend to have similar values? And this underlying principle is sometimes called the Tobler's first law of geography, where everything is related to everything else, but near things are more related than distant things. And in crime terms, this basically means that if one area has a high burglary rate, for example, its neighboring areas are also more likely to have elevated rates than, say, a randomly chosen area. Um, and this becomes directly relevant in the code demonstration tomorrow, where we basically use these neighboring relationships to fill in for missing crime areas, like missing crime counts in areas. And that's why spatial autocorrelation is fundamental to crime analysis. Um, yeah. Another very important analysis is spatial interpolation. And this is, again, kind of what we just spoke about, but it is used very closely to autocorrelation. It uses the known values of neighboring locations to estimate values in locations where the data is missing. Literally think of this as filling in gaps on a map based on what's around them. So your spatial autocorrelation does the initial which areas are related to each other, and then your spatial interpolation allows us to fill in these values. In the code demo, this is one. Yes, we do discuss this in the code demonstration tomorrow. We specifically look at one small area in the UK, which is in Surrey, and yeah, we impute these missing datas. So rather than leaving them blank or dropping them out, we can use a function called st_touches to find these missing areas and then calculate the average crime rates based on the spatial autocorrelation. And this gives us a complete data set, right? As with any type of analysis, running your secondary data analysis on missing values is of course going to affect the interpretation of results. So it's the same concept just applied onto a map. And what I will do tomorrow is plot to you the before and after comparisons of making maps with missing data and making maps with no missing data, and what this difference has on our interpretations. The last analysis technique that we'll dive into tomorrow as well is the hotspot analysis, probably the one that most people are most interested by. Hotspot analysis helps us to identify areas with significantly higher crime rates, allowing for targeted intervention. Hotspot analysis is probably, yeah, the most recognizable form, I'd say, of spatial analysis. It's the basis of any kind of map that you see in policing dashboards, news coverage, policy documents, politics. And yeah, the goal is simply to identify areas where crime is significantly more concentrated than you'd expect by chance. So in the code demo, we do produce hotspot style visualizations in two ways. We do this first using the ggplot package, and we also use the leaflet package, which allows us to produce more interactive versions of the same map. The leaflet map is the closest thing in the demo to what you'd see in real operational crime mapping tools. So it's worth paying particular attention to that section if interactive mapping is something that you want to take further after this workshop. So those are the 4 techniques we're going to be running through tomorrow. And again, I will provide some more knowledge and information through the code demo. But as I said, with crime mapping and with any sort of visualization techniques, the easiest way to learn is to do. So yes, we have a 2-hour workshop tomorrow where we get to look at these 4 techniques. Okay, just off topic, I have produced a very rough table of all the data sources for crime that you can find or that you have access to from the UK, non-UK, R packages and other. Again, one thing I really like about using RStudio is that they have available crime data just straight within RStudio, so you don't even need to download data elsewhere. You can just simply install a package and connect either an API or an open data portal, and you can pull that data, that crime data, straight into R. In tomorrow's workshop, we'll use the UK police data and we use shapefiles as well from the census. Um, but yeah, this was just in case anyone, wanted to go off and do their own exploration. These would be really good resources for you to find crime data. So there are a few main challenges of mapping crime data. The main one is geomasking and geo-privacy. And what I mean by this is that police recorded crime provides, as we said, this point information, right, through the use of GIS. But the accuracy of this spatial data is obscured by geomasking. And this is a technique that basically protects the location and privacy of victims. This is a technique called jittering. So what actually happens is when we receive a location for a crime in the UK police data source, that location is actually jittered, it's actually shaken, and the longitude and the latitude are actually shifted a little bit, which means that we don't have the exact location of where that crime is reported, which makes complete sense because we have to protect the privacy of victims. But this, of course, is going to inevitably affect the interpretation of our results, right? Because it's not exactly where that crime is to happen. This is more important or more like, yeah, prevalent in smaller units of analysis. So if you're looking at street level crime, you have to be really careful on how you make those interpretations. Of course, if you're looking at larger areas of analysis, then this becomes less important, but it's still something to consider. There are also issues with the grey figure of crime, which is that they underestimate the actual number of crimes recorded and not just reported, which again reduces this accuracy of statistical models. Um, Unfortunately, this isn't something that can be overcome in our mapping techniques, but it is again something to consider and something to think about in those interpretations. Um, there are some conceptual issues around surrounding its definition of crime types as well, which we'll see tomorrow actually. But one thing I really do despise is that police recorded crimes combine violent offences and sexual offences into one category. And this just applies a really overtly holistic definition because it conceptualizes these, I'd say, very indifferent crimes into one category? So again, what effect does this have on our interpretation of results? And then we have things like the impacts of seasonality. How has COVID-19 affected police recorded statistics, for example? Over the pandemic, researchers identified that there was a huge reduction in some criminal activity as a result of lockdowns. There was a reduction in burglary because more people were forced to stay at home, and therefore there was a reduced opportunity for crime. So if we were to hold year-to-year comparisons, we have to be careful in saying, um, you know, why crime was low in 2021 and 2020 compared to what we see now. We can't just say that there was a dip. We have to pinpoint this back to COVID-19. Can you think of any other challenges of mapping crime data? I'll give you guys just till 25 past to kind of discuss any other topics, but I will move on very, very quickly because I do want to run the GitHub demonstration about how to get our data. Um, so yeah, feel free to pop in any other challenges you think that might come with mapping crime data. I know we've discussed quite a lot, so um, no worries if there's nothing else to be said. Data availability, yes, absolutely. We are limited by what data is available. Again, mainly because of the privacy of victims. So it does become very hard to produce these kind of accurate results or statistics. And along with that, there is also we don't also always have demographic variables present from the police recorder statistics, and this is why we tend to join them with census data. But of course, there's going to be differences in the joining of these data sets. Not all crime is reported exactly. That brings us to the grey figure of crime. If anyone is interested in that, that is a kind of 101 topic in criminology, the grey figure in crime, in that not all crimes are the actual number of crimes recorded and the actual crimes reported, there's a huge disparity. Um, Getting up-to-date data, absolutely. We know exactly what it's like, but processing real data can be real challenging. For example, in the UK police data set that we're using, we're actually only using data from I think 2024 we're looking at because I couldn't get access to the 2025 data because it just hasn't been uploaded yet. Um, does it take a while to be published? I reckon so. Yes, there's a few barriers to get through, in order to be published. Um, Typically when you're making any sort of kind of crime data, yeah, you will need to talk to someone uh in either policy or in law enforcement itself. Linking crime data to demographic information. Oh, sorry, yes, I missed that point, but yeah, exactly as I said. Um, we'll see a little bit how to do that tomorrow actually, because I have a example of how we can um map crime data across rural and urban areas, and we'll see the differences in what that demographic information does for our crime data. Parks tend to not have a geocoded crime because they don't have an address. Great point. Such a good point. Because how can we address a park, right? So sometimes we think that crime has happened in a street, but it's actually happened in a park. But um, yeah, parks tend to not have open areas tend to not have an address. So what do we do with that information, How accurate is that those crimes that are recorded in those areas? Census data gets out of data quickly. Yes, yes, it does. As you'll know, we are only have access to the 2020-21 census data, which means that in tomorrow's workshop, we're comparing crime from 2024, but using census data from 2021. What effect does that have on our data? What effect does that have on our interpretations? Okay, I'm going to move on just because we've got 5 minutes left. I'm going to quickly run the GitHub demonstration, and if I've got time, I will answer your questions. But oh, we're running quite short. Maybe we can run a little bit over. Hopefully the Zoom doesn't stop, but we'll see. Um, so yes, if you want to open up your GitHub link, which I'll do here for you, this is the repository that contains all the information for the code demonstration tomorrow. There are two important folders for you, which is the data folder. This is where our census data is stored, crime data is stored, and our shapefile data is stored. If you want information about how to access that data, there's a Word doc here that has all the information needed for you, but you don't need to do that because the code workbooks, which are seen in this folder, actually just link to the GitHub URL, so you don't need to download the data yourself. But what you'll see are two files. You'll see .rmd files and .ipynb files with our four topics that we'll be covering. And if you scroll down a little bit, there is basically three ways to access this data for tomorrow. Let me just open up. First way to access this data is to clone this repository in your own RStudio. So if you go ahead and open up RStudio like so, let me just minimize that. This would be the way that I recommend that everyone does this. Oh, there's always an update needed with R. But what you want to do is simply click the big green code button and copy the HTTPS link. By cloning this repository, it means that any changes that I make here, you will have access on your own computer. You open up your RStudio as you see here. You click File. You click New Project. It might take a little while. You click Version Control. You click Git, and you simply paste that URL in the URL box. You give it a name, whatever you want to give it, and you can store this in any directory in your own computer by clicking Browse. And you always click Open in New Session, and you simply create the project. I'm not going to do that before I confuse my own computer, because I've got everything already set up here. So as you can see, everything on the GitHub is available here. So if you do it this way, we'll be working with the .rmdb files. So if you go ahead and open them up, they'll look like this. My suggestion for you is to please read the prerequisites file before the workshop tomorrow. This has every bit of information needed on how to set your working directory, to install the packages. And this is the most important part. These packages can take anywhere between 5 to 10 minutes to install just because they are very, very large packages. And this is just another con of working with spatial data. Things take a while because we're processing such large amounts of data. But yes, this is my recommended way for you to work in the workshop tomorrow is to simply clone this to your own computer. You can also, if you don't want to do that, if you're unfamiliar with that, you can also just download the zip file and yeah, download this kind of externally, but it means that you won't be connected to the GitHub page. So any changes I make on here, so for example, I'll add the slide decks at the end of the workshop, you won't have access to these and we'll have to kind of re-download it. The other option for those who are not familiar with RStudio or don't want to install extra software or are just unsure about RStudio, I've created these basically cloud-based links that allow for you to work in RStudio without having to download anything. I've done this in two softwares. One is in Posit, and Posit has allowed me to basically clone the whole RStudio into a cloud-based environment, which means you'll be able to run the workshop uh, in your browser like so. Again, to note, please read the prerequisites file. If you're working in this cloud-based environment, installing the packages in this instance will take 30 to 40 minutes on a Mac and 40 to 50 minutes on Windows. So please do this beforehand. And this is why I suggest just cloning the environment because you're working in the cloud-based environment. It can just be very slow. You will need a POSIT login to do so, but yeah, there's that. And I've also set this up in a Google Colab. For this, you'll just need a Google login. And in this instance, you can't have a full R project loaded in a Colab environment. You have to do this by script, which becomes a little bit annoying because you have to open each one individually. But again, as you can see, it's all loaded here. I would suggest making sure that you please read the prerequisites file, I can't say this enough, and install the packages before attending the workshop tomorrow. Yes, I think that's everything of importance. Let me just have a quick look at the questions. We've got a couple minutes. Well, we're a bit over time. No worries if everyone has to leave. Yeah, I'm going to try answer these questions very quickly on the Q&A function. Yes, that is everything. Thank you all for listening. Thank you all for participating in this workshop. I hope it's been useful for you. I'm excited to run through the code demonstration tomorrow. Again, please install the packages beforehand. And yes, thank you all for listening, and we'll see you tomorrow.